So, good afternoon. We have two talks today. The first one is by Emilio Ceccotti, who graduated in Bologna under the supervision of Lauro Moscardini and Gianni Bernardi, and then has moved to Groninger to Kaptein Institute for the PhD, working in LOFAR under the supervision of Ringa and Kopmans, and today will tell us about the modeling of Cygnus A. Please, the stage is yours. We remove. No.
Oh, I think it's fine.
Please do.
So hello everyone, and thank you for having me here after 3 years. It's a pleasure to be here again. And yeah, I'm going to talk about my PhD work that I'm doing at the Kaptein Astronomical Institute in Groningen with Andrea Finga and Leon Kopmans, and with the collaboration of the LOFAR team. So yeah, I'm going to talk about the an improved spectral modeling of Cygnus A using a new radio imaging method. And we'll see also an impact on the LOFAR 21 centimeter power spectrum. So I will start with an introduction of why 21 centimeter signal is important. And so we know that after the recombination, all the gas is neutral. And after a few million years, the first stars and the first galaxies start to form. They start to heat and ionize the gas. And then the gas starts to be indeed ionized, and the epoch of reionization starts. And how can we observe these signals? So the signal coming from the neutral hydrogen. Well, we have the CMB temperature as the CMB emission as a background light, and we have the clouds of neutral hydrogen during the epoch of reionization. They have a temperature which is called spin temperature, and so we have a contrast between the temperature of the CMB and the temperature of these clouds. And this brightness contrast evolves with redshift, and it maps the neutral hydrogen history, so X is term, and then the density field of the matter and the spin temperature of the gas. And as you can see from this map, we have fluctuations in space. So we can map this signal, the 21 centimeter signal, with power spectrum, studying the different power that we have at different scales. But the problem is that we are not here. The observer is not during the epoch of reionization, but we are there. And we have a problem, the foreground. So foreground is all the emission that we have in the middle, so extragalactic emission and galactic emission, like the Milky Way. Oh, I didn't say that, but 21 centimeter line is emitted at 1.4 gigahertz. So when it's emitted from the epoch of reionization and we observe it, we see it redshifted to 200, 150 megahertz. So to observe it, we need radio telescopes, low frequency radio telescopes, and we need interferometers, so radio interferometers to map the spatial scales, because interferometers are many stations of small telescopes, and the distance between these stations, these antennas, is a baseline, and the baseline maps an angular scale on the sky. So small baselines means that we can see large scales on the sky, while long baselines, so long separation between antennas, means small scales. So we can map different scales with interferometers. But the problem is the foreground, and the foreground is 5 orders of magnitude brighter than the 21 centimeter emission. And to get rid of it, we apply the subtraction technique, which means that we model the sky, in this case it's a galaxy, we subtract it from the real data, and we try to see something from the residual data. Of course, residual data have noise, so we have the systematics of the instruments, and the current instruments are not able to see the signal. So we hope to detect the noise. I know it doesn't sound nice, but we can only put upper limits on the signal at the moment, so on the power of the 21 centimeter emission. But yeah, what is the power spectrum? I'll try to explain very quickly what is the power spectrum. So to understand what we can detect with these instruments, we have to define two spaces. So the image space, so the real space, and the Fourier space. And we said that in the image space, so the real space, we have a separation between the antennas. These are the two antennas, which is the baseline. And we need to define three directions. So we go along the line of sight, and we have the sky, which has two directions, so which are parallel to the sky plane. And since the signal is cosmological, and we know that the universe is homogeneous and isotropic, we can average them together in a cylinder. So in the Fourier space, we have this K perpendicular. And then we have another direction, which is along the line of sight. And with interferometers, this means frequency, because with frequency, we can map different redshifts, and then we can map the space along the line of sight. And then we have this K parallel. So we can define a space, K perpendicular, K in parallel. That means that large spectral fluctuations stays in the low corner, while small spectral fluctuations stay at higher K parallel. And yeah, because it's the Fourier space, so it's the opposite of the real space. And the same for the angular scales. So small scales stay at higher K perpendicular, and large scales stay at low K perpendicular. But the important thing is the spectral fluctuations, because we know that the foreground, so the galactic emission and the extragalactic emission, is smooth over frequency, over tens of megahertz, because it's mainly synchrotron emission, so it's very smooth. So it should stay at very low K perpendicular. But then we have a problem. We observe this foreground with some instruments, then we have foreground, we have mode mixing, the instrument is, it has chromaticity, and then this foreground leakage leaks to higher K parallel, generating what we call the foreground wedge. So in this wedge, we expect to see the foreground emission. But above it, everything which fluctuates very rapidly in frequency, that means the 21 centimeter emission, because it's a line, so it fluctuates quickly, it should be free. And then we would be able to observe the EOR signal in that window. That's something to take into account when we are going to see the real power spectrums.
Sorry, my ignorance here. That particular shape or the foreground wedge, is it instrument dependent, or it's general to every different?
It depends on the instrument, in the sense that K perpendicular essentially is the baseline, right? And the baseline is not the baseline, but it's the projected baseline along the line of sight. Yes. That becomes the UV plane, and this UV plane depends on the frequency. So that's why we have this shape, because K perpendicular, the baseline increases, but then we have the increase of frequency along the K parallel. Then it generates this shape. So it's not, it doesn't change with the instrument, but depends on how the instrument is designed. Okay. So it depends on how many baselines we have with that lens. It's a bit complex, but yet we have a dependence between K parallel and K perpendicular with a baseline, essentially with a frequency. If we move to the LOFAR UR, so LOFAR is a radio interferometer located in the Netherlands with many stations across Europe. And the UR project focuses on mainly two fields, tritium-196 and the NCP, so the North Celestial Pole. And they were chosen because here, as you can see, the galactic emission, this is the galactic emission on 400 megahertz, is quite low in that field. And there are not many bright sources close to them, so it's easier to do the foreground subtraction there. And in 2020, the latest upper limits were published from the NCP field. And here is where the problem started, because I told you that we are aiming to detect, let's say, the noise. So we want to set upper limits on the noise of the instrument. And the noise here is the green line. But the upper limits that we are seeing, so the values, are the orange points. And we have an excess power. So we are few factors higher than the noise. And we are trying to understand what is the reason of it. It can be some residual foreground, some calibration errors, ionospheric effects, radio frequency interference. And in my work, I'm focusing on the residual coming from the foreground subtraction. In particular, I told you that there are not many bright sources in these fields, but still we see that there are some bright, I don't have a pointer, but some bright emission close to them. And even if they are far, we can still have them in the field of view of the instrument very far. So the field of view is like a sinc function, and in the lobes, they can enter, these very bright sources can enter the instrument, the field of view, with side lobes. And I'm talking mainly about ATIM sources. So in the radio frequency, low radio frequency, the ATIM sources are quite famous because they are in the north sky. They are sources brighter than kilojansky, 1 kilojansky. And for the NCP field, the most important sources are Cygnus A and Cas A. So we have a radio galaxy, Cygnus A, and supernova remnant, Ceccotti A, and they have 10 kilojansky fluxes at 150 megahertz. It's a lot. And yeah, in my work, I focused on the Cygnus A modeling. So Cygnus A is a radio galaxy, is an FR2 radio galaxy. It's a typical galaxy with 2 lobes. And it has a spectral energy distribution like this. So it's like a power law with a curvature, and yeah, with a curvature at low frequency. But the most interesting thing are the hotspots, because it was shown in 2014 that the hotspots have a curvature, so they have an inverted spectrum at lower frequency, and they account for almost 20% of the total flux, which is not so negligible. Why am I saying that? Well, because if we go to look at the model that the LOFAR project was using for these papers, for that paper, is this. Okay, it's not very clear, but every line is a component of the model. So you have the position of the component, the total flux of the component, but the important thing to focus on is this. So this column, this is the spectral index of each component, which is minus 0.8. It's fixed, so there is no variation over the source. And this is not what we know, because we just saw that the hotspots want a positive spectral index. This is not minus 0.8. And the total spectral index is minus 0.67, which is even flatter than minus 0.8 that model gives. That's where we want to use a new method that we developed. This is a paper that I published in August last August. It has a lot of jargon, so if you have any questions, please ask. So this method uses a pre-existing spectral index map to force the spectral indices of each clean component during the multi-frequency deconvolution, fitting a logarithmic polynomial. That means that in radio, with interferometers, with LOFAR, we have a wide band in frequency. We split this frequency into narrower channels, and we fit these channels with some function. In this case, this logarithmic polynomial. And instead of fitting the spectral index and the curvature, or even higher orders, we force them. So we fix them with an input map, which can be obtained from your previous data or from the archive. So it's you are free to use any kind of spectral index map to transfer this information into your model. And here I quickly show how it works. So we have an image, we make a spectral index map, which becomes the input map. And when you use this map as input, you see that the model, which is in the same format of before, so each line is a component, you see that the spectral indices are exactly the same of the input map. That's what we want. I think I will go very quickly on these results. This is the results from some simulations. And on this column, on the last column, we have the results from the full spectrum compared with normal linear polynomial fitting. The first line are the spectral index map coming from the models, and we see that the four spectrum outputs are much better than the other ones, and even the residuals are more uniform than using usual polynomial fitting. And the same is for observations. Well, actually, it wasn't the same at the beginning. So you see that if you use the four spectrum method on not calibrated data, the residuals, so this is the standard deviation over frequency, you see that the residuals are quite higher than normal polynomial fitting. But when we use the output models to calibrate, we see an improvement of all the residuals. So they became a bit more comparable to the normal polynomial fitting, the linear polynomial fitting. But let's go back to Cygnus A. So this is the new model. This is the new image of Cygnus A obtained with LOFAR-HBA mid and high data, so between 110 and 250 megahertz. And this is the spectral index map on the top and the curvature map on the bottom. It's quite noisy, but what I want you to focus on are the hotspots. So now in this spectral index map, we see that the hotspots have the spectral index values that they should have from the McKean et al. 2014 papers. And also the curvature is negative. So when we use this map as input for the force spectrum method, what we get is a new model. Yeah, again, this. But you see now that the spectral indices are physical. They have values more reasonable. They vary with across the source. And yeah, here I show the residuals, see the same plot as before. And you see that here, with no calibration, we didn't do any calibration at this point, using the force spectrum results in lower residuals than using logarithmic, than using linear polynomials. And that might be that, might mean that the data itself wants this kind of modeling. And this is the model. This is the new model, high resolution with 400 components between Gaussians and points. But I didn't show you the old model. Well, I showed the table, the model, but yes, this is the old model. So on the left is the old model. So it's very low resolution. It has very weird shapes. It's Gaussians with zero length axis. And comparing it to the new model is very high resolution. Yeah, because the old model was obtained with LBA data, so lower frequency than low resolution. But there is also a shift in the coordinates, which is confirmed. So it's confirmed, it's not to be confirmed. But this means it's not a big problem because during calibration, we can take care of this shift. But still, it means that the old model is not that good. Then finally, we can go to see some results. So we tested the new model on some simulations. So we simulated the NCP field plus CAS A and Cygnus A. And for the NCP, we use a simple model with 600 components instead of the 10,000 that the NCP field has. And for Cygnus A, we use the new model. So we assume that the new model is the real sky. And here you see that it's quite different from before because we have the primary beam applied. And then we have this shape also because it's quite far from the phase center of the field. And then we apply the current processing pipeline using the old Cygnus A model. So we want to see, assuming that the new Cygnus A model is the real sky, how the old model behaves compared to it. I will talk very briefly on how the calibration steps work during the LOFAR UR pipeline. So this is the usual radio interferometer measurement equation. So it's the equation used for calibration because the data that we get from the antennas from the interferometer are not calibrated. They are completely off. But we have a model visibilities. We have the model, and we need the gains to bring the not calibrated visibilities toward the model visibilities. And we do this in 1.5 steps. So the first step is the direction independent calibration. That means that we solve with using a single model of the NCP. We don't consider Ceccotti A and Cygnus A, and we use the old model as a single direction. And so we get one single solution for the world field. And we apply this solution to the data, and then we do a direction dependent calibration. That means that the model is split into clusters, so in different directions. We find a single gain for each of these directions simultaneously. We also add Cas A and Cygnus A, and we don't apply these solutions to the data. We apply them to the model visibilities, and we subtract this combination from the data to do what we call indeed the foreground structure. And this is what we see. So this is before direction-dependent calibration, and the lower one is after the direction-dependent calibration, which is not real calibration, it's more like corruption. And this is noise-like in the NCP. This is what we want to see, because in the simulation we also use this noise. But yeah, then we move again. Okay, we move again to Cygnus A after the direction-dependent calibration, and we see that there is a difference using the old model and the new model. Yeah, because we also do a run using the new model to see how it works. And we see that using the new model, the residuals are a bit better. Probably you don't see it, but Cygnus A is very confined here. So the residuals are a bit wider, but the ripples, that's the ripples that goes into the NCP, so they leak into the NCP, are lower than using the old model. And in the old model, we have a very deep negative and a very bright positive. But let's look at the power spectrum finally. So on the left, it's the direction independent calibration power spectrum. So we still have the foreground emission, and the lines are the Cygnus, where Cygnus A should be. And after we subtract the foreground, so after the direction dependent calibration, we see that in the wedge, so in the lower part, the foreground is the NCP emission is very low. We still see something, the middle power is Cas A, but Cygnus A is very well subtracted using the new model. And it's more clear if we look at the ratio between the new and the one. So blue means better in terms of the new one. And we see that at higher K perpendicular, the new model behaves better than the old one. This is even more clear if you look at the spherical power spectrum. So at low K, the difference is not so high. So this is old minus new from that plot. And we see that, after K of 0.2, the difference starts to be something important. That's good, but when we go to the observations, this difference is not, because we did the same for the observations where we don't have a real model. So we use the new model and the old model, and the difference is not so bad. So we see that, for example, at K 0.2, the new model is worse. Yes, this is still old minus new. So the new model is worse than the new one, but a difference of 300 is okay, but still is not enough to solve the excess power. That means that it might be different effects causing it, maybe the primary beam, because it's the only thing that we use in the simulations that can cause this effect. And we are still trying to investigate it. I don't have a concluding slide, so thank you.
So questions from the room or the remote audience?
I have a curiosity. So are there implications for the physical modeling of the source due to the new model that we create? So the fact that we have a new model to represent the source, has that also implication on the physical interpretation of the mechanism of the emission?
Not really, because we made the model knowing the physical interpretation of it, not the physical, but the physical properties of the source. So we know that, for example, we need the curvature in the hotspots, and we try to have this curvature in the model, which were not in the previous model. Of course, this data, the data that we got after the 4-spectrum method applied to the Cygnus A data, can be used for some physical interpretation. This is not what we do, but actually it's something that can be done. Also because these observations are more high, they have higher resolution than previous ones. So it can be possible to do some things. Yeah.
Sorry, a couple of questions. The first one related to this one. When you say that you follow the model to be the one that you essentially know by literature, you said something like that.
Yeah.
You simply are somehow renormalizing your slicing, your spectrum within the band. Did I get it well?
Well, we extracted a spectral index map from the data,
Yeah.
and we saw that the spectral index map agrees with the literature.
Agrees. But they are not the same. Because you said that the best fit is different. I mean, the intrinsic one that you get from your data may be different. You forced to be the same. If I get it.
Not really, in the sense that if you use a simple polynomial function to fit the data, the model that we get from this kind of fitting might be different from what we get. The point is that during fitting, we have a lot of other systematics coming in, like, I don't know, for example, at the edges of the band, the fitting doesn't behave very well, so can changes the spectral index.
My second part of the question is very stupid. Did you try to use your fitting, the same procedure, instead of having me see how it works? I mean, because you're right, you may have a lot of spurious effect, but maybe they are getting some information about some noise that you have in your observation. I still think that people to go try to understand if something is getting this.
We didn't, because usually we extract models from different observations and then use these models to calibrate NCP observation, for example. We never try to extract A-team's models from the same observations that we are using for 21 centimeter power spectrum extraction. But that might be an idea. Yeah.
Okay, unless there are questions from the remote audience. Okay, I think we can stop here at the first talk. Thanks.
Sarei curioso di vedere i suoi dati veri.
No, abbiamo fatto anche dati.
No, infatti, cioè usare.